Hello everyone, we are Group 3 and today we'll be presenting our idea, Web Crawler. This is a brief overview of what we'll be covering today. So as we all know, or rather don't know, walking on the moon is hard. In fact, the first few astronauts that traversed the moon all had trouble walking due to the difference in gravity experienced on the moon. After which, engineers from Boeing designed a special car that was able to traverse the land, allowing astronauts to cover more land and more moon sites to further their studies and research. Soon after, however, moon exploration with astronauts stopped due to lack of technology as well as budget limitations. But the lunar roving vehicle at the time was a revolutionary device due to its tires, which were made of a woven mesh of zinc-coated piano wires and titanium threads which riveted in a chevron pattern and prevented the wheels from sinking into the lunar soil. This later paved the way for other exploration rovers such as Spirit Opportunity, Curiosity, as well as most recently Perseverance. As such, today, most explorations are conducted autonomously with the help of advanced technology through rovers like these. These rovers are equipped with multiple sensors and tools which allow them to study space rocks as well as send footage back onto Earth. So what is the problem? In the last 60 years, much of the moon's surface has been explored and studied from astronauts to autonomous rovers. Yet, what's beneath the surface is left untouched and unknown. In order to explore beneath the surface of the moon, rovers will need to travel through what we call lunar lava tubes. These lava tubes on the moon were formed during the eruption of basaltic lava flows. There is observational evidence from the Japanese Kaguya spacecraft which shows that these lava tubes exist in the Marias Hills region. Lava tubes may potentially serve as enclosures for human habitats. These natural tunnels provide protection from cosmic radiation, solar radiation, meteorites, and much more. They are insulated from the extreme temperature variations on the lunar surface and could provide a stable environment for human inhabitants. Current rovers in use, like the Perseverance, are not equipped with the necessary tools and are incapable of navigating through these small lunar lava tubes.
Our solution makes use of current successful methods, as well as our own unique features, in order to create a robot which is not only able to traverse long distances across the moon's surface, but also navigate its way through lunar lava tubes. Meet Web Crawler. Web Crawler is a synergy between two lunar robots. First, the surface rover travels from the lunar lander to the shaft of interest. When it arrives just at the edge of the shaft opening, the surface rover will open its compartment, and the web crawler will exit the compartment of the surface rover. The web crawler will be connected to the surface rover with a cable consisting of tension ropes, as well as data and power wires. The winch on the surface rover will slowly unreel as the web crawler descends into the shaft. Upon achieving contact with the ground of the lava tube, the web crawler will explore the surroundings and collect rock samples using the onboard drill and scoop. To ensure stability while drilling, the web crawler is also equipped with gripping claws. Environmental data is downlinked to Earth via the surface rover for monitoring purposes from the control station. It can also receive commands from the control station via the surface rover, which also transmits power harnessed from the solar panels to the web crawler. The web crawler then autonomously returns back to the opening of the shaft, and the surface rover will reel it back up. It then goes inside the surface rover to deposit the samples before exiting again to conduct further exploration and sample collection in the lava tubes. At the end of the mission, the surface rover will navigate its way back to the lander. This is the CAD model of the 6-wheeled surface rover and 6-legged web crawler, which uses a tripod gate movement. This animation shows how the web crawler will be housed in and how it will be wired to the surface rover. And this animation shows the gripping mechanism of the web crawler to maintain stability while drilling. This table summarizes the technical details of both the surface rover and the web crawler. Both robots will be powered by DC motors as they offer good positional control and torque. The surface rover will have a LiDAR sensor on board, as well as front and rear cameras, solar panels, a battery, and an electric winch, while the web crawler will have a rock extraction drill and scoop in addition to the sensors. For the communication system of the robots, the surface rover will be the main point of communication. Therefore, it must have an X-band transmit high-gain antenna for direct communication with Earth, an omnidirectional, very high frequency or ultra high frequency antenna to communicate with the lander, and an omnidirectional X-band antenna to receive commands from Earth. The VHF or UHF antenna not only allows backup of data to the lander, but also allows the rover to receive commands from Earth via the lander in case the X-band antenna on board the rover fails. On the other hand, the web crawler will only have wired connection with the surface rover, through which it will send data to Earth and receive commands from Earth. The navigation and operation of both robots will be controlled by a hybrid system of onboard AI and manual teleoperation from Earth. This table summarizes the main navigation and operational tasks that the robots are required to complete. For the surface rover, it has to be able to navigate from the lunar lander to the shaft of interest and back. It also has to be able to release and reel in the web crawler in sync with its movement. For the web crawler, it has to be able to exit the surface rover autonomously, explore around the lava tube, collect rock samples and environmental data, navigate back to the shaft opening, and return to the surface rover to deposit the samples. The hybrid AI teleoperation system consists of an onboard AI on both the surface rover and the web crawler to complete most of the tasks while following a predefined plan. It will have access to high frame rate and high resolution data on board. Thus, it will be able to complete the task accurately. However, the AI will still be continuously monitored by the control station on Earth, which has to work with limited near real-time data. If the AI encounters uncertain situations, it will automatically switch to manual teleoperation mode, giving control to the control station on Earth. Although control station will have to work with limited data, humans are able to make more informed decisions based on the context of the situation. The transmission delay is approximately 2.5 seconds, which is not too bad due to proximity between Earth and Moon. The AI will be built based on behavior trees as they offer better reactivity, modularity, and flexibility over finite state machines. In the development of the AI, it is also important to minimize the use of stateless and idempotent tasks to improve reactivity. Meanwhile, the control station on Earth will have to work with abstracted LiDAR point cloud data, as well as the relative coordinates calculated using odometry in monitoring and operating the rovers. To ensure low latency in the telemonitoring and teleoperation of the rovers, the bandwidth requirements must be minimized. To achieve this, we propose using two techniques. Firstly, traditional compression will be used on images and point cloud data, such that the only large data left to downlink is an NRT feed from one camera. At 2 frames per second and 640 by 480 resolution, undergoing H.264 hardware compression, this translates to around 50 kilobytes per second. The second technique is applying algorithms on board to convert detailed point cloud data into high-level abstractions for downlink. For example, each obstacle detected by LiDAR can be converted into a circle center coordinate and radius for downlink, massively reducing the bandwidth requirements. Furthermore, the relative positions of the lander and rover can also be simplified into 3D coordinates instead of the full point cloud. Lastly, minimizing the number of behavior logic and states will also reduce the data size for downlink.
So what makes web crawler different from other inventions out there? From our research, the only robot capable of traversing such narrow terrain is the Asagumo rover. Asagumo is the smallest robotic lunar rover at only 10 cm tall and wide and weighing just 1.3 kg. It's set to make its maiden launch sometime in 2022. Equipped with 4 legs rather than with wheels or tracks, the rover will be able to explore parts of the moon other landers cannot reach. It is equipped with cameras that have the capability to take full high-definition videos, which will be analyzed to indicate if lava tubes do have the capacity to create lunar bases. However, Asagumo's main drawback is that due to its small size and battery capacity, it will only be able to walk up to 10 meters as its first launch goal in 2022. Webcrawler, on the other hand, due to its cable connection to the surface rover, will constantly be powered by it, allowing it to travel further and deeper into the lava tube, as well as retrieve back its crawler. Here is a competitive analysis of Webcrawler to other rovers such as China's Sheng 5. As you can see, Webcrawler is more competitive and more advanced in other areas which other rovers lack. That's not to say that Webcrawler comes with any drawbacks. Webcrawler is expensive to build, and an intricate design is needed to ensure that the crawler is always connected to the surface rover with a physical wire. Nevertheless, we believe that Webcrawler is the most efficient and capable rover out there in order to tackle current moon exploration problems. As Constantine once said, the Earth is the cradle of humanity, but mankind cannot stay in the cradle forever. We hope that one day, web crawler can be implemented into NASA projects in order to potentially create a habitable human base on the moon. Thank you for listening.